Indeed, as the title says, I'm going to speak about something like polar decomposition in metric spaces. This is a joint work with Michael Różański at University of Ghent. So this is a rough outline of the talk. Basically, I'll speak a little bit about the definitions of what is what here, and then I'll present some general results, and then we'll see what these results actually tell us and what open problems there are and what is known in particular cases. So, all right. So let's begin with definitions. So what is a polar decomposition? So let's think of polar coordinates in the Euclidean space. Say in Rn, we have a certain measure, mu, which is given by a smooth density with respect to the Lebesgue measure, mu dot, right? Then when we have an integral like this, we have a locally integrable function f, and when we write the full integral over the space with respect to this measure, we can then switch to the so-called polar coordinates. So we introduce this polar coordinate r and the angular coordinates, which I collectively call phi, and the phi range over the spheres of radius r. The sphere of radius r is exactly this. And then there is, of course, a kind of a Jacobian, which appears because of the coordinate transformation, and is exactly this, right? So basically, we have a structure where first we integrate over the radial variable from 0 to infinity in this case. For every fixed r, we integrate over the sphere of radius r, right? And there is a measure which lives on the sphere. And this polarized form of the integral allows some technical advantages in mathematical analysis. So how we came to this problem actually was from applications. So my collaborator, Michael Różański, together with a collaborator of his own, Dalty Verma, they have this series of 2 papers devoted to Hardy inequalities on metric measure spaces. In their work, in order to achieve their results, what they require is the existence of kind of a polar decomposition in a metric space, which is what? So they assume that for a locally integrable function f, the integral over a metric space with respect to a Borel measure can be written in this form. An integral from 0 to capital R, this capital R may be finite or infinite, doesn't matter. Then dr integral over the sphere of radius r in the sense of the metric space, fr, and a certain measure that lives on the sphere, right? So this dr over here is pretty specific. I'll talk about it later on. It allows you to perform things like integration by parts with respect to the r variable, and that's exactly what I need to achieve their results. So when during the discussion in our group, Michael announced this as an open problem. He said, well, we have to assume this, but if there is any progress in this direction to show that such a polar decomposition actually exists in some generality, that would be a great advancement. And then somehow in a couple of days, the idea crossed my mind that why is this not just an instance of measure disintegration, right? So it turns out it is indeed a measure disintegration. It has some technical details, but in principle, this is a measure disintegration, and we'll now show how to handle that. But there are still some caveats, and we'll talk about it in a due time. All right, so we have a metric space M, a Borel measure mu. By Borel measure here, I mean just any positive sigma additive measure on the Borel algebra. I don't assume any regularity or other things which some authors assume as part of the definition of a Borel measure. I don't. So I fix a point x0 as a reference point, and then I introduce this distance function from the point x simply as the metric from that point to any arbitrary point. And then I have the spheres and balls of radius r. The sphere is exactly the pre-image of R, and the ball is the pre-image of the semi-open interval until R, and this is obviously the union of all possible spheres up to there. Then, if I have a Borel measure mu, and then I have this map rho x naught, which maps M to this interval 0 to R, there is a pullback measure, basically, on 0R, which basically gives you the measure of a ball centered at x naught of radius R. Okay, so this is kind of a measure on the real line, or on an interval on the real line, which is defined by the measure of balls. So now bear with me, this is kind of a slightly long definition, but it should make sense when we do it. So I have a metric measure space M d mu. I say that it admits a polar decomposition at a point x naught if there exists a field, a one-parameter field of bounded Borel measures omega r, depending on r, measures on M for almost mu x naught. Remember that mu x naught was this pullback measure coming from the measures of the balls. So mu x naught almost every r, such that for every measurable function f on M, for which this integral makes sense, the following conditions should hold. First, the map from R to this integral with respect to the measure omega r is Borel measurable. This is simply a standard definition of saying this is a measurable family of measures. Next, the measures omega r should be concentrated on these spheres. So the integral over the whole measure space with respect to this measure is simply an integral over the sphere for almost every r. And finally, our desired byproduct is this, that the integral over M of a local integral function, we already assume that this somehow exists, can be rewritten in this form. An integral over the radial variable. Now, with respect to this measure, d nu x naught, you can't run away from it. It's just the measure which has to appear radially. And then an integral over each sphere of radius r, fr d omega r. So if all of this happens, I say that we have a polar decomposition at point x naught. All right. So, of course, our results hold in certain assumptions. These assumptions are mild, and they are not unique in a sense that there are various combinations of assumptions that can be used to derive the same result, more or less. One crucial assumption is that all finite radius balls have finite measure, because otherwise things just blow up and it stops making sense, right? So you are dealing with integrals which are infinite. Then, well, separability of the metric space helps, but it's not crucial. So we have a main theorem which assumes the separability, but we also have an alternative theorem which doesn't assume separability but requires slightly more of the measure. Then completeness of MD is also kind of helpful, albeit not crucial. It's helpful because it helps to make sure the balls have finite measure. And then sigma compactness of the metric space, it's almost sufficient and necessary, almost, for the following little statement. So it's a simple exercise, basically, to show that every locally finite Borel measure, and it has to be locally finite in our case, because otherwise the finite balls won't have finite measure, right? So every locally finite Borel measure on a Polish space is concentrated on a sigma compact subspace. Moreover, that sigma compact subspace is actually a union of a countable locally finite family of sets which are themselves countable disjoint unions of compact sets. So it's more than sigma compact, but in particular sigma compact, right? Here, of course, Polish assumes separability and completeness, which are not necessary, but as soon as you admit that restriction, then you are basically on a sigma compact subspace anyway. So you are not too far from sigma compact. That's the message. All right, now what is our main result? The main result is here. So let MD be a separable metric space and X naught be a point. Let mu be a Borel measure on the metric space M sigma such that first, mu is inner regular, or sometimes they call it tight, which means that for every Borel set A, the mu measure of A is exactly the supremum of compact K mu measures for all K inside A. You can approximate the measure of A by measures of compact subsets of A inner regularly. And then, as I said, we have to assume that the balls of any radius around X naught have finite measure. And that's enough. So then M d mu admits a polar decomposition. This is a standard application of the measure disintegration techniques. As I said, there is a variation of this theorem where separability can be avoided, but then the measure has to be assumed to be, well, slightly more than radon. So I haven't written down this version here in the slides, but in principle you can work with non-separable metric spaces. It's just that you have to assume that the measure is slightly more regular than just irregular. Okay, but this was just part of the problem, because remember that what we originally wanted was something like this. So dr over here, but what we got is d mu x naught r. So this d mu x naught r is just any Borel measure on the real line, right? So you can't necessarily write it as something times dr, because that measure doesn't have to be absolutely continuous. And you can't apply integration by part techniques. So the question is, in which cases is that measure nu x naught actually absolutely continuous? And this question seems to be open, not well understood. So if I denote by f x naught r the function which is exactly the measure of this interval with respect to the measure nu x naught, which is the same as the new measure of the ball anyway, by definition. So then nu x naught is absolutely continuous with respect to the Lebesgue measure, if and only if this function is locally absolutely continuous, or absolutely continuous with respect on every compact interval on the real line. So if that is the case, then we can rewrite this abstract integral as a proper integral, kind of Riemann integral, if you wish, from 0 to r dr, and then this factor can be incorporated into the omega r by a redefinition. So that would solve the problem. But unfortunately, it is not known. In general, it's not even known in the simplest, some of the simplest particular cases. And now I want to proceed to discussing this question in particular cases. So let's think of Riemannian manifolds. So in a Riemannian manifold Mg, a smooth connected Riemannian manifold with its geodesic distance Tg taken as the metric and its Riemannian volume form Vg taken as the measure, then we know that for every ball Brx naught, if the Ricci curvature is bounded from below on the ball, then the Riemannian volume is finite. So we can guarantee the first condition, the finiteness of the measure of balls, by controlling from below the Ricci curvature. So we have this kind of statement: if Mg is a smooth connected Riemannian manifold with its geodesic distance dg and Riemannian volume Vg, if we assume that the Ricci curvature is bounded from below on every ball, then every Borel measure mu that is absolutely continuous with respect to Vg. Now this is a point we have to think a little bit. So the statement is true, of course, for the Riemannian volume itself, but not only. If it is true for any measure, then it's automatically true for any other measure which is absolutely continuous with respect to the original one. Okay, so this then holds for any measure which is absolutely continuous with respect to Vg. But it doesn't mean it is true for any other measure. So you need to have a certain naturality condition on the measure in order to expect that that measure provides you with an absolutely continuous nu x naught. Obviously, you take some very nice geometrical, say, objects and put the discrete measure there, and then it blows up, right? You can even actually draw a pretty nice manifold for which it blows up. So imagine that I have this curve. Say I go from here to there along a straight line, and then say this is a circle of radius capital R. I smoothly turn the curve towards here, and then I suddenly go along the circle, and let this point be x naught. Okay? So what happens? I take just the curve distance as the metric. So the dimension of SR of the sphere, here is 0, here is 0, 0, 0. As soon as it gets to R, bump, it becomes 1. So you have a jump in the measure nu x naught at here, although this is a nice smooth manifold with a smooth metric defined on it. Right? So it's not even about smoothness, it's not even about absolute continuity. This measure has to have certain naturality property with respect to the metric space in order that you expect it to have this absolute continuity property. All right, so that's why it is reasonable to restrict one to measures mu which are absolutely continuous with a very natural measure, the Riemannian measure nu g. Okay, but this is Riemannian manifolds. So since the Ricci curvature is bounded globally on Riemannian manifolds of bounded geometry by definition, basically here we have compact manifolds, homogeneous spaces, and even more generally, by Hopf-Rinow theorem, a complete Riemannian manifold has all balls relatively compact, so Ricci curvature is automatically bounded, so these conditions are kind of satisfied a priori. So on a complete Riemannian manifold, all our expectations are met. So the polar decomposition works, the measure, radial measure is absolutely continuous. This is, however, not a new result, because in a complete Riemannian manifold, you could build polar coordinates from the exponential map, and you have even more explicit formulae for that. So although by itself it's a nice result that the nu x measure is absolutely continuous, and this is a non-trivial result, although the proof is not difficult. It's just a straightforward application of the Gromov-Bishop volume comparison theorems of the volume comparison theorems of the measure of a ball in the given metric and the measure of a ball in the Euclidean metric. So the non-triviality of this is in the Gromov-Bishop theorem not in this result. The application is pretty straightforward. You get that the function fx0 is not just locally absolutely continuous, but actually Lipschitz, right? So you get even something stronger. So, but yeah, so from the polar decomposition perspective, it doesn't give anything new. So the next simplest situation where you would like to apply this would be the sub-Riemannian structures, say. And the simplest case, you take a Lie group, a left invariant sub-Riemannian structure. Can you then have a polar decomposition with an absolutely continuous radial measure? And the answer is don't know. So we have talked to specialists in sub-Riemannian geometry and analysis, and none of them seems to know the answer. So everyone expects it to be true, but we don't have a proof. So basically we take a connected real Lie group G, a radon measure mu on the group, a left invariant sub-Riemannian structure, where D is the Carnot-Gauda-Théodorin metric. Then, as a metric space, it is complete. And then the balls are relatively complex, therefore the finite measure condition is met. Also, G is sigma compact, the polar decomposition exists. So the only question is, mu x0 is absolutely continuous or not? And the answer is, unfortunately, we don't know. Okay, so this is basically all I wanted to do today. So I finished a little bit early. Hope everyone is happy about it. So this is the paper. It appeared in the Journal of Mathematical Sciences in the special issue dedicated to the 80th anniversary of the Academy of Sciences in Armenia. It is available in 2 languages. The first paper in this series, which is available both in English and Armenian. And it is available open access. So yeah, this is all I wanted to tell you about today. Thank you very much for your attention.